Tonight we're going to do modeling with quadratic functions. So we've been using the quadratic functions a lot. Now we're going to see how they affect the real world. So we have an object that's fired upward, initial velocity of 112 feet per second. Units are important here. Its height in feet above the ground as an object, as a function of time. So that means our variable is t. In seconds, since it's fired, is given by this equation right here. So first, at what height was the object fired? So we will go through when it was fired. That is time of 0. So h of 0 equals negative 16, 0 squared plus 112 times 0. 0 feet. 0 times 0. We're right on the ground there. Then we're going to graph the equation. I might have put a little backwards there. So, new screen, negative 16x squared plus 112x. We graph that, and it's two straight lines. That's no good. So first thing I want to do is think about it. We're talking about things being thrown upward. I'm going to just guess that the max is somewhere around 200. And that was a pretty darn good guess. So we can see that right there. So when I'm graphing this, go to the table, Control T, and we're going to have the point 0, 0. I'll make a table for us. $196, $2, $160, $3, $192, $4, $192, $5, $160, $6, $96, and $7, $0. So good and bad news about that. 1, 2, 3, 4, 5, 6, 7. Hits in nice spots there. As I'm looking to graph this, when I'm over here and I see that there's two 192s, I know I didn't hit the maximum. So I want to go back to the graph. Let's get more space here, so get rid of the table. And I'm going to say Menu, Analyze the graph, and I'm going to look for the maximum. And I can see why it didn't show up. The maximum is 3.5196. So that right there is the highest point. And because it was halfway, that's why it didn't show up for us there. Next, so I paused so you would not have to listen to me count. And I labeled each y here going by 20s. So 196 right there, 2 160, 3 192, and then the 196 happening at 3.5. Then it's going back down, got an extra dot there. Show that it's curvy. Okay. And it says determine algebraically here the first time the rocket reaches the greatest height and what the max height is. Label these. So first, we know now, based on our graph, that it's at 3.5196. If I needed to show algebraically, which they're stating right there, I'm going to use what's called the turning point formula. So negative b over 2a. Going back up here, my a value is what sits in front of the x squared, and the b is what sits in front of the x. So I would have negative 112 over 2 times negative 16. Type that in, you'll get 3.5. So this fancy schmancy right here, x equals negative b over 2a is the turning point formula. that tells you where the max is. So x equals 3.5 seconds that it reaches its max height. And now to find the max height algebraically, I'm going to say h of 3.5 equals negative 16 times 3.5 squared plus 112 times 3.5. And we already know that's going to be 196 feet. Okay, so we've labeled, we're going here, and then determine when the rocket hits the ground. Okay, so here, when we had max height, what max height was. Now we need to figure out where it hits the ground. We can see right there, 0 happens at 7. How am I going to do this? I'm going to set my function equal to 0 and use the zero product law. I'm going to look at these numbers. They're both even, so I could do 2. I could do 8. So 2 times 8, I can do 16. I'm even going to pull out a negative 16, and I can see I can pull out a t, and I'll be left with t minus 112 divided by 16, 7. So negative 16t equals 0. T minus 7 equals 0. So I'm dividing my negative 16, and there's the 0. Yep, that's when I started, so 0 seconds. And more importantly, 7 seconds is when it hits the ground. Right there, hits the ground. Okay, so now we have a skateboarder half pipe ramp. Looking at this, they want us, it's given by that lovely function. Use your calculator to help sketch a graph of the half pipe, label its height at the endpoints and its minimum point. So just go ahead. I'm going to start fresh, so it brings me back. 0.06 x squared minus 1.2 x plus 7. And I can see part of it right there. They tell me that it has a horizontal distance of 20. So I'm going to change that to 0. Change that to 20. I can see that it's going up higher. So I'm going to go to the table. And at 0, it's hitting at 7. And that, at -1 it is bigger, but I can't have a negative length, so I won't have to worry about that. So I'm going to move along, go down to 20, because that's how long they said it is. And 20, it's also at 7. As I go through, it's getting smaller, getting smaller. We definitely have a min right there at 10.1. So one, two, 16. Okay, it was not enough. All right, sorry, I had to listen to me count that time. So when we're going here, counting across, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I have the point 0.07. I have the point 27, 20 comma 7. I have the point 10.1. There's my parabola. Okay. Oopsies. We have a min at 10.1. We have a max at 27. And we have a max at 0.7. So I have my endpoints and I have my minimum point. Now we have the crazy caramel corn. Here we go. Modeled by that lovely function right there. First, we want to decide algebraically the temperature that has the highest percentile of kernel pops. So that is my turning point again. So T equals negative b over 2a. This is my a, this is my b. Type all of that in, and that's going to tell me 350 degrees is when I'll get the best percentage. Now, in B, we're going to graph that, and it's saying P is greater than, oh, we have to find out what percentage. I'm so sorry. So first, determine the temperature we need. We need the temperature of 350, and then what percentage that will pop, that plugs into our formula here. Now plugging in for our T value. Type that right in, I'm going to get 96%. So we're going to graph on the calculator, and we're going to see important factors. Even though it's saying P is 0 to 1, we're going to go up to 100%. We know that that happened at 350, 96. When I type it in, we'll just start a new document because that was just no fun. Okay, so fraction negative 1 over 250 x squared plus 2.8 x minus 394. All right, nothing's there because, well, it's big. So we were talking about up to 100%, so change that to 100. We know the min is at 350, so I'm going to say 700. That's double, and there it is. We can see it's beautiful. So we have the intersection points right here of 195 and analyze graph, get a 0. .505 is my other 0. So when I'm labeling here, this can go out to 500, so 100, 200, 300, 400, 500. I'm going to have a 0 right there. I'm going to have one right before there. And then we'll go by hundreds this way, 100, 200, 300, 400. We know that 350, we're going to have the max right there. All right, and then it says using the 0 command, determine to the nearest degree the two temperatures when P equals. We did that. Look at us. We found our zeros first. Okay, typical batch has 800. So we decided we have to figure out how much does the complement expect to pop. So we set up here 96%. So 96% of the 800 are going to pop. So 0.96 times 800 is going to equal 768. So now the last question. They want at least 85, 678 kernels, if you will. At least 85% of them to pop. Write an inequality. That's going to ensure that this would happen. So now we're going to take our formula and it's got to be greater than or equal to 85. So now what I'd like you to do is use your prior knowledge. We've set this up. First thing you're going to do is subtract the 85. Then you're going to think about how you could factor that. We already know certain things. Use the graph to help you, and we will